Hello, everyone, and welcome to the EDCON Hack Workshop, brought to you by CryptoChicks and LinkTime. The topic of today's workshop is Plasma 101, and it will be delivered to you by our mentor, Kelvin Fichter, contributor of Plasma. In our Plasma 101 session, we'll be going through all the basics of Plasma, including general design patterns and building blocks. Then we will take a look at the landscape of Plasma, including Plasma MVP and Plasma Cache, to get a better understanding of what's currently being built. Also, please note that EDCON Hack is open for registration. Don't miss it. You can register at www.edcon.io/hackathon. Please note that this workshop will be recorded and you will be revisited future at our website. Please make sure to follow us on social media. You can see our websites, our Telegram channel, Facebook, Twitter, and so on and so forth. And I will paste this information in the chat window for you as well. At this point, I would like to pass it along to Kelvin, who will be talking about Plasma.
Awesome.
Thank you, Kelvin.
Yeah, thank you. Hey, okay, so I have given this presentation before, but basically the topic of this is Plasma 101 and the Plasma framework in general. So I'm just going to dive right into it. Let me share my screen. Go. And let's present this. Okay, and can everyone see that? All right. Are people seeing my chat as well, or how, I don't even know how this works. Okay. Cool. So yeah, this is the Plasma framework. Basically, some general background, and I think this is really important before we start talking about Plasma. We have these really cool blockchains, right? And effectively what we're doing here is we're fixing all of the world's very rusty financial plumbing, right? We have financial systems that are running on programs that we built in the 1970s, and this is fixing all of that. Get rid of this sound. But the problem with this is that the way we've designed these systems, they're really slow. And I'll talk about why they're so slow in a minute, but we need them to be really fast, right? We need them to handle thousands, if not tens of thousands of transactions if we actually want them to act as replacement for our financial plumbing. We have currently systems that can handle all of the, say, credit card transactions in the United States, and blockchains just can't do that. So, we have this scalability problem. Why are blockchains really slow? It's because they get really, really big, and the faster that you transact, so the more transactions that you put into your blockchain, the faster you get really big, right? So actually, sorry, I'm gonna bring up my chat again here, just in case. Cool, great. Right, so the problem with this is that the average person doesn't make very many transactions. But the way that current blockchain systems work is that in order for you to be sure that your money is safe, you need to verify everything that's happening in the blockchain, right? And if you have thousands and thousands of transactions, and each one of these transactions is, it's actually a piece of data, and it's a certain number of bytes. The more transactions you have to store, the more things you actually have to verify, and your computer starts to have to get really, really beefy in order to actually verify this stuff. But the average person doesn't make a lot of transactions, and people tend to transact within these small circles, right? If I'm if I'm in my neighborhood, there's a few places that I'm typically going to be spending my money, and it's less likely for me to be spending my money, in some other city unless I happen to be there. And then a final observation is that most transactions that are going on aren't even relevant to the average person, right? Money tends to flow within these circles, like I just said. And so a lot of the time there's money flowing that never even touches me. But the problem is that currently the way that these blockchains work, I actually have to go and verify that information. So now it's a question of how do we solve these problems, right? So layer 1 scaling basically says, okay, well, the base layer obviously isn't fast enough, right? It can't handle enough transactions. So let's figure out a way to make it faster. And there are plenty of ways to work on doing this. And currently the big things that people are working on in the Ethereum space are things like sharding, which basically means that you have, instead of one base layer, you have many, many different base layers, and you design it in a way that the security of the system doesn't sort of get split heavily every time you create a new shard, right? You get more throughput, but you still get similar security levels, right? You can also do things like add better, more efficient consensus mechanisms. So consensus mechanisms are, it's this process of how do we decide what the actual blockchain is? How do we decide what the blocks are actually going to be? And if you have more efficient consensus mechanisms, less information has to flow back and forth in order to make these decisions, and then you can make decisions more quickly, and you don't have to store as much information. Right? The other thing that we can do is create more efficient data structures. So we can literally improve the actual blockchain itself by saying, users are storing a lot of unnecessary information, and we can represent the same thing in a more efficient way. And so that lets you process more transactions. And then I guess the final thing is block size increases. This is another type of scaling. And this is probably something that people are more familiar with. There's more stuff than this, but I think these are sort of interesting things that a lot of people are looking at right now. The thing with layer 1 scaling is that it's extremely important in the long term, but governance can slow down the rate of innovation. On the base layer, things just have to move more slowly because the stakes are that much higher, right? If you make a poor decision about how the base layer is going to work, then all of a sudden you've just potentially lost money for very many people. And especially when we're talking about multi-billion-dollar protocols, these decisions need to be made in a very, very careful way. So onto layer 2 scaling, right? We have this thing, this observation that it's just not easy to improve the base layer, right? But it's much, much easier to build things on top of the base layer, right? No one's stopping me from building an application on the base layer. People can stop me from making a change to the base layer, though. So what a lot of people have sort of realized is you can scale things by moving things off chain. And what that basically means is that you're making transactions that sort of interact with this other blockchain, but they're happening somewhere else, right? They're not, all of that transaction data doesn't actually have to go onto the blockchain in order for this idea of, a transaction has happened to make sense, right? Where the main blockchain, the Ethereum, can basically recognize that a transaction has happened without the whole transaction actually going onto Ethereum. And so the design space for this is varied, right? I think the three main things are basically side chains, state channels, and of course Plasma. And these are I believe that these are kind of the three fundamental off-chain designs, as well as some other more recent things, but I would consider them more layer 1 systems, and we can talk about that maybe later. So I think in order to understand Plasma, it's really important to understand sidechains first, because Plasma, I think, kind of came out of this evolution of seeing sidechains as potentially problematic in certain ways and wanting to develop more secure systems. So a sidechain, for people who aren't familiar, is effectively a blockchain that runs alongside of another root blockchain. So usually that root blockchain in my world is Ethereum. And so this means you have these two blockchains running next to each other, and things can kind of go from one blockchain to the other, right? You can take a thing from over here and you can send it over there and back and forth. And so what you'll do typically is that users will transfer stuff from the main blockchain to the sidechain, and then they'll transact on the sidechain, and it's usually much, much cheaper. And then eventually, you know, when they're done transacting on the sidechain, they'll move their stuff back to the root chain. The fundamental assumption of these sidechain systems is that the consensus mechanism on the sidechain actually works, right? So this is, you know, whatever the consensus mechanism is, maybe it's a proof of authority system, maybe it's a proof of stake system. The problem is that if this thing fails, you can either have assets stolen, you can have assets locked up permanently, and it, you know, effectively it becomes impossible to move things back to the root chain. And the other problem is that it's also effectively impossible to move more complex things onto the root chain. So let's say I have a smart contract on the side chain, and the side chain, or for some reason I want to move the smart contract onto Ethereum. That becomes effectively impossible. And of course, the reason why these sidechains are even cheaper than the root chain is because they are less secure than the root chain, right? You're paying less money because it's less secure. And so it's entirely possible that this consensus mechanism fails and you get lost, or your funds get lost. And so it becomes sort of a calculation in your mind of how secure is this sidechain, and how much am I willing to lose if something goes wrong, or how much do I think that something might theoretically go wrong. And so for relatively low value things, you might be more comfortable. You might be more comfortable taking that risk. And I think there is a strong niche for sidechains where it's sort of this economic calculation of, am I willing to take the risk of everything falling apart? But then we have Plasma. And so Plasma is basically this, you know, the thought process behind it is, okay, so it's really cool to have these multiple chains. Obviously, you know, not having to do everything on the base layer is a really, really good idea. But we still want to provide certain guarantees. Like, we want to make sure that your funds are safe. You know, people didn't really like this idea of if the sidechain fails, all of your funds are gone, right? So you want to make sure that in the absolute worst case scenario, right? Let's say that the sidechain consensus mechanism fails, you can always move your assets back onto the root chain, even if the consensus mechanism is explicitly trying to cheat you. So I just got a question in the chat, said, why is it impossible to move contracts from the side chain to the root chain? So it's not necessarily impossible. It's just very difficult, especially when the sidechain contract has very, very complex state. So let's say we're talking about, and we'll actually talk about this more in the future, but let's say we're talking about a huge smart contract like the MakerDAO set of contracts, and a contract that holds a ton of state. If you want to move that contract from the sidechain to the root chain, you have to carry all of that state and all of that code over. And if it's a lot of stored information, that can be really, really expensive. It can take a really long time. And generally people just don't do it because they just stick with the assumption that the sidechain consensus mechanism is going to be safe. Okay, so back to Plasma. Basically, we want to provide these guarantees, and we also want, you know, hopefully it should be cheaper than making transactions on the root chain. Otherwise, there's kind of no point. And so then the question is, well, how do we actually achieve this, right? So this looks a lot like a sidechain, but it has these two extra guarantees. And I guess we'll get to that. Basically, the thing is that Plasma is not a magic bullet. When you add extra rules, you also add these interesting constraints that we'll talk about later. And certain things are easier than others, right? Certain things you can do on a sidechain that are almost impossible to do on a Plasma chain. But the reason that they're almost impossible is actually also sort of what makes Plasma chains so secure. And we will talk about that. So starting off, to actually dive into what these Plasma chain designs look like so that we can sort of understand what provides these security guarantees. We're going to talk about minimal viable Plasma. And minimal viable Plasma is sort of the very first attempt at designing a Plasma chain. This was, I guess more than a year now when this was originally published and designed. But effectively, the way that this works is that users deposit funds into a smart contract that sits on Ethereum, and users receive equivalent funds on the Plasma chain. And they receive those funds in the form of an unspent transaction output. So on the Plasma chain, literally, a block is created where there's a transaction that has one input, and it comes from nowhere. It just creates money out of thin air, and it creates funds for that user depending on how much money they deposited into the smart contract. And then the user can transact on that Plasma chain all they want, and then they can eventually, if they would like to, they can withdraw those funds, any funds that they have, back onto Ethereum. And we want to ensure that when we do this withdrawal, that users who are following the rules can't be cheated, and users are allowed to leave at any time, no matter what, right? Just that's sort of a fundamental thing. Even if the consensus mechanism fails, they should be able to leave. So consensus mechanism, what do we even mean by that? Basically, we mean the sort of process that, or the people or the group of people or the machines that periodically create blocks, right? So blocks in a blockchain are these set of transactions, and we have to sort of designate somebody whose responsibility it is to collect transactions into this bundle, and then publish the bundle and say, okay, these transactions are now part of the canonical set of transactions. These things actually happened, right? And that mechanism, in the traditional blockchain world might be something like proof of work, where we kind of assign somebody based on this lottery that gets played, where you do a lot of random computations, and then maybe you get lucky and you get to create a block, right? But these consensus mechanisms can pretty much be anything. And so especially on a Plasma chain, it doesn't necessarily have to be proof of work. We can create a proof of stake consensus mechanism. We could create a proof of authority consensus mechanism, right? Just assign somebody to just, person A is responsible for creating Plasma chain blocks. It can really be anything. And when they create these blocks, effectively what they do is that they sort of create a commitment to these blocks. And a commitment is sort of this cryptographic idea where it allows me to create a very compressed piece of data that I can actually use to then prove things about the thing that went into that piece of data. And that's really important when we want to prove to Ethereum about things that happened on the Plasma chain. So for simplicity, usually these consensus mechanisms, we just kind of hand wave it and we think of them as a single operator. This is sort of like Plasma magic, because we have this property in Plasma world that in the worst case scenario, everyone can still get their money out. It's really easy to just think of the consensus mechanism as a single operator because it's totally fine for that to be the case, right? It could absolutely just be a single operator, and and users would still be safe. So we get these benefits of sidechains, right? That it doesn't require all the participants to be live and cooperating for transactions to occur, right? So in state channels or payment channels, for example, the sort of fundamental thing there is that the consensus mechanism is that everybody signs off on every single transaction. But in this case, since we're giving that responsibility to somebody else, they just have to be online. Nobody else necessarily needs to be online for things to progress. And the other thing that we get that's sort of similar to sidechains is that the cost to actually attack the sidechain, or the cost to attack the plasma chain increases as the consensus mechanism on that plasma chain becomes more robust. So you can imagine that most long-term solutions will probably use something like a proof of stake consensus mechanism and not a proof of authority. So now we're getting into the really important part, which is how do we actually achieve this feature that if there's an attacker, that you're always safe, right? Basically, we introduce this idea of exits, which is just sort of a fancy way to say withdrawals. And these withdrawals can be challenged, right? So we'll talk about that in a second. And the idea of these withdrawals is that you play this sort of game, this sort of economic game that gives money or gives assets to the users who are actually playing by the rules and actually own those assets or have the right to withdraw those assets, right? So this is basically what exits are, right? It's a user wants to withdraw something from the plasma chain. It doesn't matter. You can basically represent anything on a plasma chain. It could be money. It could be a CryptoKitty. It could be a wallet. It could be pretty much anything. And I want to actually withdraw that thing from the plasma chain and move it back onto the root chain. And so the way that this works is that a user who wants to withdraw something makes a claim about the current state of the plasma chain to the root chain, right? So the root chain, the only thing that it has access to is these commitments that the consensus mechanism has published, right? It has access for every single block. It has a little piece of data. And using that piece of data, users can prove things about the state of the plasma chain, right? So they can literally say, I can prove to you that I had a kitty at block 123, and I'm claiming that I still own it. And I want to withdraw it because I own the kitty, right? But that claim could be refuted. So somebody could say, actually, wait a minute, you sent that kitty to me later on, and here's a transaction to prove it, right? So I can sort of present this transaction, and I can say, look, I can prove that it was included in this other block, and so you lied. You don't get to withdraw that money, right? So why is this important? Well, the answer is that you only want users to withdraw things that they actually own or that they actually have the right to withdraw, right? A user shouldn't be able to withdraw an output that they've spent, and a user shouldn't be able to withdraw a CryptoKitty that they've sent to somebody else. That wouldn't make any sense, and it would make the system unsafe if somebody could withdraw something that they already sent to me, right? Only I should be able to withdraw that thing. So here's a thought experiment. No need to actually comment on it, but I think this is interesting to think about. In all of these cases, who should actually be the person who can withdraw, right? In a simple unspent transaction output with a single owner, we probably want the single owner to be the person to withdraw it, right? That sort of makes sense. With a wallet with a single owner, it also sort of makes sense for that single wallet owner to be able to withdraw the funds. But if we're talking about a multi-sig wallet, things start to get more complicated, right? Should this be, any one of the people in the multi-sig is allowed to move the multi-sig back to Ethereum? It would still be a multi-sig on Ethereum, but do 5 people have to sign off? Can it just be one person who gets to withdraw it? So things already start to get more complicated. And then the final thing is, let's think about an ERC20 contract. How does that even make sense? Who gets to decide that the actual contract moves over? Because no one really owns the ERC20 contract. People have tokens inside of that contract, but you can't kind of point to somebody whose responsibility it is to withdraw that contract back to Ethereum, or who should be allowed to. And so this is sort of the problems with exits, right? That every single object in the Plasma chain needs to have this property that they can always move back to Ethereum, right? And it's easy to say that the owner of an unspent transaction output can exit that output, but again, who gets to exit the multisig or who gets to exit a smart contract? You have to start defining these custom rules for who gets to withdraw these things. So this is basically why generalized Plasma is difficult. But I think that a lot of progress is being made on this subject right now. And so I'm working with a nonprofit called Plasma Group, and we have a lot of awesome work on this, and we're currently creating more detailed write-ups for a design that we think actually supports a lot of this functionality. So basically, working inside of this Plasma framework means you have to break objects into things that actually make sense, right? So I don't know who gets to withdraw the CryptoKitties contract. That almost doesn't really make sense to me. Like, why would you move the whole contract over? I think a better design pattern is that everybody gets to own their own kitty, and then if I want to, I can move my own kitty over. That seems like it makes more sense in my head. And most of the current designs sort of stay within this realm, right? So Plasma MVP has unspent transaction outputs. It sort of makes a lot of sense mentally that these, it's very easy to point to who owns that output. Plasma Cash has NFTs. It's very easy to say each of these NFTs has an owner. I realized very late that these slides don't even have Plasma Cash information on them. And so I'm just going to explain it in a nutshell really quickly, because it's actually a relatively simple concept. But basically, the way that Plasma Cash works is that everything is represented as NFTs, right? So everything is represented as these little tokens. And those tokens can be anything, right? Those tokens could be a certain amount of money. They could represent a CryptoKitty, whatever it is. But when I send people money, I'm effectively sending them these non-fungible tokens. And so instead of being able to send you arbitrarily, let's say, 10 ETH, I would have to send you a 10 ETH token, right? And the sort of interesting thing with how Plasma Cash was designed is that every single Plasma Cash token is assigned a unique identifier. And that unique identifier tells you where in the sort of tree of transactions, let's see if there's a better way to explain this, sort of in every single block, for every single asset, you basically say, coin with the ID of 0 was either spent or not spent, and then you say coin with the ID of 1 was either spent or it wasn't spent, right? So you're sort of explicitly saying when these transfers happen. So I can see in every single block whether my CryptoKitty was spent or wasn't spent, right? And especially what we want to do is we want to take the IDs, or sorry, we take the asset IDs, and that actually tells us where in the tree we put that information, right? So every single block is sort of composed of a Merkle tree. And that Merkle tree is composed of this, like, the leaves are basically, was this thing spent or was it not spent, right? And if I have coin ID 0, it's always going to be in the leftmost piece of the tree, right? Or if I have coin with an ID of 100, it's always going to be in the 100th position. You can think of this as a big list. It's always going to be in the 100th position of the list. And the really interesting thing about this is that for my individual asset, all that I have to do is look at the 100th position of every single block, or let's say I'm talking about asset 100, I have to look at the 100th position of every single block. But I don't care about anything else that happened in the block, right? It's the only thing that's relevant to me, the only thing that can actually impact my asset is things that were placed at exactly the 100th position. And that means that I no longer have to actually download everything. I can now just download the one thing that I care about, which is this one specific position in the block, right? And you end up downloading significantly less data, and it becomes sort of a more scalable version of these plasma chains. The problem, of course, fundamentally with this design is that everything is represented as non-fungible tokens, which is sort of a weird model of making transactions. It's relatively simple if we're talking about, like, I want to send you a CryptoKitty, but if I had to send you 100 ETH by sending you a 75 ETH coin and a 5 ETH coin and a 20 ETH coin, that in my head it makes no sense, when on Ethereum I could just very easily send you 100 ETH no matter what, because we have this account-based model, right? So that's basically the sort of 101 on Plasma Cash. And then a lot of the research that came after that was basically, how do we make Plasma Cash support more fungible things? And that's where things like, if you've heard of Plasma Cash Flow or Plasma Prime, all of these different things, the basic idea is that we can transact many different assets simultaneously. And so instead of having to send you 100 ETH coins, sorry, 101 ETH coins in order to send you 100 ETH, I can sort of batch that and send you all of these things simultaneously. The mechanism behind that doesn't really matter, but the sort of important thing is that these new designs are sort of strictly better than Plasma Cash, but they still give you the same sort of nice properties, which is that you have to download significantly less data. You have to basically only download the data that's important to you, and no longer do you have to download everybody else's data. So basically, smart contracts are really cool, right? Currently we just talked about Plasma MVP and Plasma Cash, and those just do sort of basic payments, or basic token asset transfers. But we don't want to launch a new Plasma chain for every single new application, right? If, let's say, we want to do transfers with certain conditions on them, right? That this transfer is only valid if this other thing happened. Today, previously, the way that you would have to do this is you would have actually had to go and build a whole new Plasma chain just for that specific thing, right? And that's way too complicated. You have to build a smart contract, you have to build a client, you have to go and audit that smart contract, you have to do all of this work, and it's just too much, right? It doesn't make sense that if imagine you had to, every time you wanted to build a new blockchain application, you had to build Ethereum from scratch. That makes no sense. And so what we've been working on lately is trying to figure out a nice solution for this. Basically, we've been working on general purpose plasma chains, which means that basically users get to custom specify the rules on that plasma chain. The plasma chain itself sort of becomes a very basic, simple shell, and other people can then build additional logic on top of the plasma chain, which means that if you wanted to change things later on, you don't actually need to change the plasma chain. You just add more logic. You effectively just write a new smart contract. And generally, the way that this ideally should work is that there's high-level languages that make sense, and it should feel like writing smart contracts on Ethereum. And this is sort of the current state of the art in Plasma world, and more detailed write-ups will be coming soon. We're working on that really hard right now. And hopefully people here get to start writing Plasma Chain smart contracts. Cool. Any questions? I think that was the meat of my 101. Okay, so one of the questions here is, Loom seems like they solved the generalized plasma thing. Loom's plasma is one of the approaches that you're going to try. How is generalized plasma different? Are generalized plasma different from Loom's? Can I comment on that? Yeah, sure. So Loom is actually working on a plasma cache chain. So they're not actually working on generalized plasma. Currently, the way that Loom's design works is that they have a sort of side chain where you can put smart contracts, but then they have a plasma chain which sort of only supports non-fungible token transfers. And so when you're on the side chain, you get, quote, side chain security, which means what we were talking about before, that you're sort of trusting the side chain consensus mechanism. What we're building is effectively a way to build some, basic smart contracts that provide you with, or off-chain smart contracts that provide you with plasma chain security, which means that in the absolute worst case, you can get your money back, which isn't true on Loom's plasma, or on Loom's sidechain design. Does that make sense? Okay, the next question is, will your tools allow for customizable plasma clients as well? Yeah, so what we've actually built, and if you're interested, there's our GitHub is, well, I can put it in the chat later, but it's github.com/plasma-group. And one of the things that we've put there is this thing called Plasma Core, which is sort of the core functionality for our plasma chain clients that's super extensible. You can sort of program your own logic on top of it all you want, and you can add this different, you can add these sort of smart contracts directly into the client very easily without a lot of extra work. And that's sort of something we've been working on really hard. Cool. Any other questions or things that you would like elucidated further?
Okay, guys, while you're thinking, let me talk to you about our upcoming workshop. Our next workshop will take place on February 26th, February 28th, Thursday, and it will be at noon Australian time. The title of the workshop is Using a Viper in a JavaScript World. It will be delivered by our mentor, Ben Jones, a researcher of Plasma Group. And to remind you again, this workshop, it was brought to you by CryptoChicks and Link Time.
Awesome. Okay, so to answer two more questions that have popped up in the chat, how are the terms sidechain and plasma chains related to each other? So again, basically the difference between a sidechain and a plasma chain, they're similar in the sense that it's kind of like this other blockchain that runs alongside a main blockchain like Ethereum. But the primary difference is that in a sidechain, you're making different security assumptions. In a sidechain, you're fundamentally trusting the consensus mechanism of the sidechain. Whatever it is, maybe it's a proof of authority, proof of stake, whatever. The security of your funds are fundamentally reliant on that mechanism being secure. However, in a plasma chain, instead the assumption is we don't assume anything about the plasma chain consensus mechanism. It has to exist for the thing to run, but if it fails, we can still be secure. The only thing that we're assuming is that Ethereum is safe. which is a very different assumption, right? It's usually that assumption is stronger than saying that the sidechain is safe. Another question is, can we have special logic on the plasma chain? For example, if A sends something to X, then X will split the coins into B and C. And the clarification here is A, B, and C are users, X is the special address. So yes, actually, in a way, basically it's difficult to do this for a single coin, right? It's kind of annoying to split a single coin. Usually the way that we're thinking about this currently is that let's say I own 10 coins. The way that this would work is that I actually, instead of owning 10 individual coins, I own sort of one range of 10 coins. And then I can create a special transaction that sends half of them to user B and half of them to user C simultaneously, right? And I can easily do more complex things with our current work, which is, maybe I could even turn those coins into a payment channel or something, and then at the very end of the payment channel, they get split based on the final balances, right? So you can do very complex things with this new construction. Questions from the social media. What will be the future of Plasma from your perspective? So this is really interesting. I've had a lot of discussions about this actually quite recently. And my theory is that a lot of the current designs will sort of merge into one larger design. People are kind of realizing that everything that people are working on in Plasma world is very similar, right? Plasma MVP and Plasma Cash end up actually being very similar from sort of if you look up high enough, they look really similar. And all of this work on this generalized Plasma stuff is kind of saying, let's go back to basics. Let's simplify what Plasma really is. And let's take all of the complex stuff and put it, sort of as a sub level of the Plasma chain. And so my theory is that there will be sort of really big Plasma chains that their whole job it's not to send money all over the place. Their whole job is to basically aggregate the commitments or the sort of state transitions of sub Plasma chains, right? So if you've ever seen the original Plasma paper, there's this whole weird tree of Plasma chains thing. And I think it's only quite recently that people have sort of started to think about designs that actually can make that a reality. And I think it's actually very powerful. So hopefully just trees of like nested Plasma chains. And hopefully something more general than what we have right now, because basically the MVP and cash designs are too specific. They're too focused on payments, and it's more important to be focused on just general transactions, and we can get payments within that. Cool. Any other questions?
All right, if no more questions, I would like to thank Kelvin for delivering this great presentation today. And I would like to thank everyone for attending it. I hope you enjoyed this workshop, and we're all looking forward to seeing you at our next workshop. Have a great day.
And if you have any additional questions, feel free to reach out on Twitter. I'm at Kelvin Fichter. My name is on the slides. Or by email, first name, last name @gmail.com. I'll respond. Or on Telegram as well. I'm at ETH Research.